This video shows the derivation of the Laurent series for a function that's analytic on a region that is not simply connected. So suppose f is a function that is analytic outside a disk of radius r, which means the absolute value of z is greater than r. So, give you a picture. Here's the real and imaginary axes. Here is a radius r circle, and f is analytic outside of this circle. And the point is, our goal given a z with z greater than r, so maybe it's out here somewhere. The goal is to find a series representation for f. That's the goal. And the point is we cannot use the Taylor series because that would require f to be analytic inside a disk that's at least of radius z. So cannot use Taylor series because we don't have, and I'd say don't necessarily have, inside that disk, or near z equals 0. And I should say the series we're after should be centered at z equals 0. It's of course the case that we could move that center somewhere else. That changes the series in a relatively easy way, so we're not losing much generality there. We could also have a differently shaped region, so not necessarily outside of a disk, and maybe it might be bounded somehow. These things kind of add some complexity, but the complexity is not really very fundamental. This is the most fundamental form of the problem, and you can derive all the generalizations fairly easily. So I'm just going to show you this most straightforward version. Okay. So unfortunately we can't use the Cauchy integral formula because of the Cauchy integral formula requires a simply connected region. We don't have that. But we can kind of work with it in kind of a similar way, where let me draw you a bigger picture and kind of carve it up into nice schematics so you can see what's going on. So here's our origin. Here's our radius r circle. Here's the point z that we're interested in. What we're going to do is we're going to take that point z and we're going to draw another radius circle. Let's pick a different r. Let's call it radius epsilon circle. We can vary that epsilon however we like. And inside, that fits inside a larger circle. I don't really care to mark the radius because we don't really need it. Now these circles are oriented in a particular way, and really I'm going to be worried about analyticity inside this annulus shaped region. F is analytic inside this region. And while r is given to us, epsilon is not. So this is not given, and so can be chosen at will. And in fact, we will do just that. And furthermore, I haven't set orientations on any of these boundaries. I'm going to do so in the following way. I'm going to orient the outer boundary counterclockwise. And I'm going to orient these two inner boundaries clockwise. Now what that does for me is it allows me to make use of a slight generalization of the Cauchy-Goursat theorem, which tells me that the integral of an analytic function on a simply connected region is always 0. And this is not a simply connected region because of the hole, the radius r business going on here. So we can, however, we can do the following. We can cut the region, like so, and orient this boundary like this, and like this, noticing that these green boundaries that I've added cancel out when you compute the integral along them. And if you were to follow around, say starting out here and moving around the outside, and then finally coming back and around and whatnot, you end up with a simply connected region. The Cauchy-Goursat theorem will end up saying that the integral of f in that region is in fact 0. Now we don't actually want f, we want something a little different. Let me make the observation that the Cauchy integral formula applies to the radius epsilon circle. But since I've oriented the boundary backwards, i.e. clockwise, it says the following. It's got an extra minus sign. So minus 1 over 2 pi I times the integral around this circle here. Let me name my boundaries. I'll call this one C. 1, call this one C2, and call this one C3. So the integral backwards around C2, f of s minus z dz. Well, f is actually analytic inside that whole region. So the Cauchy integral formula does apply there, and that's f of z. The minus sign is because of the oriented clockwise situation. Okay, so that's something we know, and actually this kind of tells us the integrand we'd like to use. If you notice, this integrand that I've written, in particular the f of s over z minus s, this integrand, this is analytic everywhere except for one spot, that being where z is. So analytic everywhere f is analytic except not at z. So given that integrand that I've got there, really I could apply this Cauchy-Goursat theorem to the whole thing. So that means I should be able to write out an equation relating this integral along C2 with the other two integrals. Now the integral along C2 of this integrand, with the minus 1 over 2 pi I in there, is f of z. So it'll allow me to figure out what f of z is and write it out in terms of these other two integrals. At that point, those two integrals we can rewrite in terms of sums and get our series representation. That's the game plan. Alright, so let's do that. Let me show how that works. I'm going to take this selfsame integral here around C2. So let me go grab it, copy it, next page, paste, there you are, and now I'll do a little cleanup. I think I can do this. There we go. Okay. So that's there, but now I'm going to write this guy out a little differently. You will notice that C2 integral is oriented clockwise, as is C3. So C3 is going to look pretty much the same thing, except it's going to say C3 on there. And f of s, s minus z, d, s. Oops, this should have been ds, and up here as well. Okay. Alright, so that's C3. Now C1 is oriented opposite of all of these guys, so that's going to come in with the opposite sign, i.e. it's going to come in with a plus sign. 1 over 2 pi I, interval C1, f of s, s minus z, ds, and all this thing is equal to 0. This is the Cauchy-Gorza theorem. That tells us this is 0. Okay, now, we already know this first term in this sum is equal to f of z. This is really f of z here, we know that. And so if I move the other terms over to the other side, I'll get a 1 over 2 pi I, integral C3, f of s, s minus z, ds, minus, now this C1 integral, alright, and that's a C1 integral. Now we have to kind of figure out what these guys are, and here's some observations. Due to the geometry of this problem, when I'm on the C1 integral, you will notice that where is s? S is somewhere on C1, anywhere on C1 I like, and notice it's farther away from the origin than z is. So strictly when we're on the C1, s is greater than z in magnitude. Now, on the other hand, on the C3 integral, the opposite is true, because z is outside of this circle of radius r, where we're having all of our non-analyticity, or potential non-analyticity. So the situation is reversed there. Okay, this suggests that our strategy for dealing with the power series is pretty much sort of opposite. I'm going to want to do the same kind of algebraic tactic that one does when cooking up a Taylor series using the Cauchy integral formula, namely factor out something from the denominator, recognize that it's a geometric series, rewrite it as such, and then kind of reassess what happened. That's still largely what we want to do. But it's not entirely, because we got to do it in two opposite directions. So in the first integral, the C3 integral, I'm going to want to ensure that I end up with something that ends up with a, dare I say, a geometric series with a ratio less than 1, so that it converges. So I'm going to want to factor out the bigger thing, namely the z. So if I factor that out, I'll get a, an s over z, and minus 1. And over here, I'll want to do the opposite, factoring out an s. So you will notice now that I basically have two geometric series floating around, one with an s over z and one with a z over s. Now, of course, the geometric series formula, recall that, it looks like an r to the n equals 1 over 1 minus r for absolute value of r less than 1. Okay, so you will notice in particular that it's a 1 minus r kind of thing. All right, we don't have that in the first series. Fine, but we can just pull a minus sign out. So let's do that. You will notice that I get a minus 1 over 2 pi I. Both of these have that minus 1 over 2 pi I. And let's do that. Keep hitting that button. And the second integral now looks about the same in terms of signs, which is largely good. Okay, now let us make use of our geometric series. Geometric series in the first case is going to be for s over z. It's going to be s over z to the n ds. The second integral is of course going to be the opposite, as I've said a bunch of times. And perhaps I should make that an m rather than an n, because both of these guys are in play, and we don't want to mix up the indices. Okay. There we are. Now, a little bit of regrouping is probably wise. So the thing to notice here is that in the first guy, this first guy, I have f of s, s to the n over z to the n plus 1, and that's summing, n equals 0 to infinity, ds. The second guy, summing m equals 0 to infinity, f of s, z to the m over s to the m plus 1 ds. Okay, now we've already dealt with a series like the latter term, the second term, and in the Taylor series situation. And so now what I need to do is I need to figure out how to deal with the first series. And the lesson here is actually an indexing problem. If I mess around with the indices a bit, everything can kind of play out the way it should. So here's the thing. Notice the z powers go z to the 0, z to the 1, z to the 2, and so on. Over here, when I put in an n equals 0, I get a z to the n plus 1, a z to the 1 in the denominator. So that's a z to the minus 1. As n goes up, the denominators go down, and so on. So you'll notice actually the z's in powers actually string together rather nicely. I get all of the negative integers showing up in the first sum for powers of z, and all the positive integers and z to the 0, the constant term, showing up in the second sum. So if I rewrite that first n in terms of m's, where I've run my sum, instead of going from 0 to infinity, go from minus infinity to minus 1, then actually these two sums will be compatible. That's not a bad observation there. Now I still have these integrals floating around, but that's fine. If I formally, for the moment, pull out this sum and run this as n equals 0 to infinity, let me copy here. 1 over z to the n plus 1 minus 1 over 2 pi I, and related. That's the first sum. And then the second sum is here. Oops, that's not what I meant to write. Z to the m with this minus 1 over 2 pi I integral C1 f of s over s m plus 1 ds. Okay, so that looks pretty decent. So if I now string my indices together, re-index that first sum to go m equals minus infinity to negative 1, this is now going to be z to the m out front. Now what goes on inside here, of course, has to deal with that change as well, because now my m's have become, or n's have become m's. So this is now, well, the first s, this would be s to the 0. So in fact, what I should do is run that guy up there over s to the m plus 1 ds. Now they're all compatible. Now the neat thing about this arrangement, as you can probably see, is that now I formally have the same integral, of course different contours of integration going on, but that's pretty convenient. So what this really means is, this really means that I get all these negative powers of z coming about from integrating around C3. Where is C3? Oh, C3 is the guy in the middle. What about C1? C1 is the guy on the outside. So this works like, put in quotes, Taylor-like terms. And this one here is kind of like negative exponent Taylor like terms. I think the best way to actually write this down, if you want to be really compact about it, is to say that the whole thing is really a sum that goes from minus infinity to plus infinity. And there's some coefficients, Cm, z to the m, and these Cm's is, well, you know, these minus signs are kind of irritating. These minus signs are a product of the orientation of the contours, so don't let that bother you too much. I'm going to leave a box there to say that that's really either C1 or C3, depending on whether you're looking at a positive, or rather a negative or a non-negative m. This whole result, this whole thing is called a Laurent series. They are the, or perhaps a Laurent series for f. Of course, the reason for the equivocation about this being a or the is because I can move the center, and then I will certainly get different coefficients. Now the point being, the difference between a Laurent series and a Taylor series is that the Taylor series doesn't have the hole in the domain. The Laurent series does. What does that mean? Well, it means that you can have problems at the origin, and that's okay, you'll still get a series. What kind of problems do you have? Well, for one thing, problems that happen, failures of analyticity at the origin. What is that going to be? Well, that can be answered. When you look at the Laurent series, that's all those negative terms. So if you will, this guy here is really analytic, sort of the analytic part, and this is really the not analytic part. Although that's kind of intuitive in a sense.